Hello math students, inverse functions. Recall that y is a function of x if for any one x coordinate there is only one corresponding y coordinate. And recall that x is a function of y if for any one y coordinate there is only one corresponding x coordinate. We say a function is 1-to-1 or 1-1 if y is a function of x and x is a function of y. Plot each relation below and identify which relations represent 1-to-1 functions. So our relations are just a collection of four ordered pairs only. The first one, we have 1, 5. Let's plot 1, 5. Notice our scale. 2, 7 is right here, 3, 6 is right there, and 3, 8 is right here. To determine if y is a function of x, we want to do a vertical line scan. So we imagine a vertical line, we imagine that vertical line scanning the graph, and every time we intersect, we pause and ask, are we intersecting how many times? But here we have an intersection of two different points. So we would say that y is not a function of x. Y is not a function of x, so it's not 1-to-1. We have to have y being a function of x and x being a function of y. And I'm going to actually just write it out, not a function of x. Next example, we have 1, 5 again, 2, 6, 3, 5, and 4, 7. Okay, so this graph does pass the vertical line test, but it's going to fail the horizontal line test, right? So if you draw a horizontal line and scan your graph with it, we have a horizontal line intersecting twice, meaning that if we try to think of x as a function of y going backwards in the table, we have 5 yielding multiple outputs. So when you're thinking x is a function of y, you think x is input, y is output, input, output, but we have 3 yielding multiple outputs. That's why y was not a function of x, because we had an input x that yielded multiple outputs for y. And here we have the issue that 5 is going to have 2 different x's that go with it. So that means x is not a function of y. But y is a function of x, but x is not a function of y. So again, not 1-to-1. You have to have a function both ways. And let's look at the last one. You can probably guess what's going to happen here. We have 1, 5 is a point, 2, 6 is a point, 3, 8, and 4, 7. Okay, notice that this collection of 4 points passes both the vertical line test and the horizontal line test. So we do have y is a function of x, and we have x is a function of y. So we have a 1-to-1 function. Notice that 1-to-1 functions pass both the vertical and horizontal line tests, in that no vertical line and no horizontal line intersects the graph more than once at a time. This is how we're going to identify 1-to-1 functions pretty easily when we have continuous functions, not just collections of dots. Okay, let's go to the next slide. An object is launched straight up. Its height in feet after t seconds is given below. The graph of the function is also provided. Do the following. Give the domain and range of this function. Okay, so this function starts at this time 0 and ends at this time here. So we would say that the domain is t has to be somewhere between 0 and 4, inclusive. Or you can write t as an element of bracket 0, 4, bracket. What's the range? Well, the range is what the h's are, all the different possible h's. Well, the two endpoints, h is 0, and then we have the highest point right here at the middle. Looks like its coordinates are 2, 64, and so 64 is the highest. So our range is that h has to be between 0 and 64. Or you can say h is an element of the interval from 0 to 64. Fill in the table using technology. Okay, so here's our image. Let's change our vertical scale so that we can see it a little bit better. And if you want, you can do your cropping. So we're going to do this special brackets, and we're going to say t has to be greater than or equal to 0, but less than or equal to 4. So that gives us the cropped image as well. Okay, now we are expected to find h when t is 0. Well, that's obvious from the data. If you plug 0 in, you're going to get 0 back. You can see that from the image and from the rule. Plug 0 in for t, you're going to get 0 back. So at time 0, the object is a height 0. At time 1, I think it's pretty clear that from our data that this point here, 1, 48, appears to be the point. Easy to confirm. Plug 1 in for the t's, and you should get 48 back for the height. 2 seconds after it was launched, it hits our peak height, 64 feet, this point right there. Now we're going to go backwards in the table. Give me the t's when h is 48. That's this line right here. That's this height. We can see that there's a second time when the object has this height, time 3. So there's another t. Other than the 148, there's a 348. What about 32? Here's where the technology is going to come in handy. We can see that there are 2 different times where the height is at 32. Using technology, I'm going to make a horizontal line, y equals 32, and then just click the points of intersection. And we see we get 0.586 and 3.414. So there are 2 different times where we had a height of 32. Now, given our discussion about 1-to-1 functions, if we do a vertical line and then scan the graph, there's only ever one height for any one time. This passes the vertical line scan. which means that h is a function of t, which was actually given when I use this notation. But the horizontal line test, the graph fails because there's lots of horizontal lines that intersect the graph multiple times. And if you think of this as going backwards, 32 had multiple outputs. If you think of 32 as the input, every height between 64 and 0 has 2 different times. So it's not a function going the other way around. So you would say t is not a function of h. You tell me height and you get multiple t's. So this is not a one-to-one function. Okay, let's go to the next slide. There are 2 systems for measuring temperature, Celsius, which is C, and Fahrenheit. F will stand for the temperature in degrees Fahrenheit. Fill in the first 2 rows of the table. So a little bit of physics review here. Celsius is a useful temperature system because it's easy to remember the freezing point and boiling points of water. 0 is the freezing point of water. And in Fahrenheit, that's 32 degrees. And then water boils at sea level, I should say, at 100 degrees Celsius, which you may or may not know what it is in Fahrenheit, but it's 212. Now we're going to express F as a function of C. Let's plot a few points here, 0, 32, and this doesn't have to be to scale. Let's say this is where Celsius is 100 and Fahrenheit we say is 212. We'll just say that's 212. The other point is 0, 32, so here somewhere. And then we have a line. The relationship between them is linear. So let's go ahead and figure out what the equation of this line is. So you can pretend like this was just like x and y, and we're going to use our point slope form. Let's first get the slope. So the slope will be the change in y over the change in x. In other words, change in f over the change in c. And in this case here, 212 minus 32 is 180, and the change in c is 100. This is 18 over 10, which is 9/5. One of our points given is a y-intercept. It's a vertical intercept. So we know our mx plus b structure. It's going to be f equals mc plus b. And here's part b. We've got to give the domain and range. Okay, well, there's something called absolute zero, which occurs at approximately negative 273 Celsius. So we can only go so far back as Celsius being negative 273. But then in theory, let's say the temperature can go up as hot as possible, which means I do want to figure out what the corresponding Fahrenheit temperature is. So we're going to plug negative 273 in for this C right here. So it's a negative 459.4 Fahrenheit. Let's go ahead and fill this in. This technically is the lowest possible Fahrenheit. So we're going to say our domain is C coordinates. What's the lowest possible C? And that is going to be negative 273. And then we'll say up to infinity. And then the range is going to be the F, the Fahrenheit, which is the output. The lowest it can be is this negative 459.4 up to infinity. Okay, part C is express C as a function of F and give its domain and range. Okay, so for part C, all we have to do is take the answer we have for part B and solve it for C. So we're going to say F minus 32 is equal to 9/5 of C, and then multiply both sides by 5/9. So C is equal to 5/9 of F minus 32. And this answer is part C, except we got to give a domain and range. So now F is the input and C is the output. So when I say domain of this function, I want to give the F's. So whatever I said was true about the F's up here in the range, I can paste and copy, and that's now considered the domain of the reverse direction. And whatever I said for the domain of the first function, I can say is going to be the range of the reverse function. I've done A, B, C. We can fill in the rest of the table now. So I have 2 different functions. One is a function that tells me how to go from C to F, right? So when you're in the table and you want to go from C to F, I'm going to use the first function I created, input C and output F. So we plug in a C equals 20 right into this area right here. So C goes in 20, divide 20 by 5, that's 4, times the 9 next, 36, and then add 32, we get 68. Now if I want to go the other direction, if I want to go from Fahrenheit to Celsius, I'm going to use this second direction function. So I'm going to start with F equals 86 and plug it in right there. 86 minus 32, do that first. That gives me 54. Do 54 divided by 9, it's 6. And then times 5, that gives me 30. If I want to think of the input as Fahrenheit and the outputs as Celsius, then I use this second function. If I want to think of the input as Celsius and get an output in Fahrenheit, I use this function. And then the role of domain and range switch, because in the first function here, domain is the Celsius and range is the Fahrenheit. In this function, it's Fahrenheit, that's the domain, and Celsius, that's the range. And then is this a one-to-one function? Well, look at the graph. This is a linear graph. It's a ray. It's a line that starts at a point and goes forever in one direction. But all diagonal lines and portions of diagonal lines will be one-to-one. They'll pass the vertical line test and horizontal line test. So this is a one-to-one function. Functions that are one-to-one are also invertible, which means that the function is reversible. The reverse function is called the inverse function, represented by f raised to the minus 1, as demonstrated below. So if you have a function that takes you from a to b, then the inverse function will take you from b back to a. It just reverses the flow. So we could have said that in the case up here, this is my function of c, which gives me degrees Fahrenheit. So this function down here we'd call the inverse function, and it inputs capital F. So going this direction, we use little f. Going that direction, we use the inverse function. So you can see that if you try to plug in 100 into little f, you're going to get 212, because little f takes c's and turns them into capital F's. And the reverse direction would input the 212 and output the 100. So this is what we're trying to say here, that if f is a function that turns a into b, then the inverse function should turn b back into a. So use function and inverse function to describe the Celsius-Fahrenheit relation. F of c, let's use g instead of f. The f can be confusing because we have capital F as well. Let's say g of c. G is the function that tells me degrees Fahrenheit. It does 9/5 of c and then adds 32. The inverse function inputs f and outputs c, and it's going to be 5/9 of f minus 32 in parentheses. You could, of course, distribute that 5/9 and not have parentheses, but I'm going to leave it with the parentheses. Use the table below to do the accompanying tasks. What do you observe about the domain and range of a function and its inverse? Find f of 3. So in this table, y is equal to f of x. So this tells me that to go from x to y is f, but to go backwards will be f inverse. So when you see f of 3, this 3 should be interpreted as an x coordinate. So we want to use this row of data right here. F turns 3 into 8, and that 8 is a y coordinate. Find the domain and range of f. Okay, well, if f is the direction that treats x like the input and y like the output, the domain will simply be all the x coordinates that we see in this list, and the range will be all the y coordinates we see in this list. And I'll write them in order. Now when you say, okay, look at this table, so what's f inverse of 6? Well, f inverse inputs y coordinates, so you want to think of that 6 as a y coordinate, and we want to use this row of data, because that y coordinate will be turned back into an x coordinate of 2, and that 2 is the x. So the inverse function treats all of the y's as the inputs and the x's as the outputs, meaning that the domain and range are going to simply switch. The domain is the y coordinates and the range is the x coordinates. Okay, let's go to the next slide. Suppose a function triples an input and then adds 2. Describe the steps for the inverse function, then represent each symbolically. All right, so imagine if you start with a number, you triple it, and then you add 2. The question is, how do you undo that? How do you reverse that process? So if f triples, then adds 2, then the inverse direction should first remove the 2, then do the reverse of tripling, which is times 1/3. So symbolically, f of x. F takes an input, and let's say it gives us a y coordinate. F takes an input x, it triples it, and then it adds 2. Well, the inverse should take the y coordinate and turn it back into an x coordinate. So we're going to get an x coordinate by doing f inverse of the y coordinate. And we want to remove 2 and then times 1/3. So we're going to take the input of y, remove 2, and put the 1/3 here in the front. So the first one triples x and then adds 2. Yeah, that's the default order of operations there. But if I want to remove 2 and then multiply by 1/3, I have to have the parentheses. Now I should also say that if you take x and y out of it and just say that f inverse of y equals 1/3 of y times 2, and you think of y as a dummy variable, you can really put anything you want here. If you take the x's and y's out of it, and just think of what does the function do to a thing, it doesn't really matter what letters you put here. I could put a w here and just put a w there. I can even get confusing and call them both x. I don't like doing that because if you call them both x, it gets especially confusing, because look at up here in the Fahrenheit situation. What if I had called these both c's or both f's? Then it would be extremely confusing because the variables represent an idea. But when you're doing naked math, which is math without a context, and you just think inputs, outputs as numbers only, then the function f triples the input and then adds 2. Inverse function removes 2 from the input and then times 1/3. And I'm just using x to represent a general input. Now, this commonly done is to write the function and its inverse in terms of x. I do not like doing this. I'm going to say that this function here produces a y coordinate. Therefore, this inverse function inputs that y coordinate and goes back to the x coordinate. And the way to go from one equation to the other is going to be as easy as solving for the other variable, which is exactly what this next paragraph is about. Define the rule of the inverse function, solve the original function for the input variable. Do this to confirm. And here are the steps we follow. Let's say f of x equals 3x plus 2. The first thing I would do is change the f of x to y. Then the next thing I would do is solve for x. So I'm going to subtract. So we're going to get 3x equals y minus 2, and then multiply each side by a third. And then replace x with the inverse function notation. Find the inverse function of the inverse function above. What do you notice? If I start with what I just boxed, so the first thing I would do is change the f inverse function to another variable. Let's go back to x. I don't want to use y though, because y is the input variable, so don't use y again. Then I'm going to solve this for y. So triple both sides. You get 3x equals y minus 2, and then add 2. And we get right back to where we started. This is just showing that the inverse of an inverse goes right back to the original. So we really should say that the two functions are inverses of each other. F and f inverse are inverses of each other. G and g inverse are inverses of each other. Now, since inverse functions reverse the effects of each other, it follows that if you compose them, you should get total cancellation. Because look back in Fahrenheit. If you take the number 100 and plug it into the little f function, which is this first. So take 100, plug it into little f function, it'll turn it into 212. We'll take 212 and plug it into f inverse function, and it'll turn it back into 100. So when you do the two-step process of a function with its inverse, you should get total reversal and get back what you started with. And it doesn't matter what order you do the composition. So f composed with the f inverse, if you start with a, you end with a. If you do the reverse composition, you start with a, you end with a. Confirm this for the inverse functions above. Okay, so let's do f of f inverse of a using the f and f inverse we have up here. This really means we're doing f of f inverse of a. So I'm going to first calculate f inverse of a. So right there, it just changed the y's to an a. So we have a third times a minus 2. Now we want to plug that into the f function. So this plugs in for this x right here in the f function. So the f function is 3 times x and then plus 2. The f function triples the input and then adds 2. So if the input is this, so we're going to triple the input and then add 2. But when you triple this input, so you're going to first triple the third. So that will cancel. So you just get the parentheses all just become a minus 2, but then there's a plus 2 after the fact, and you go right back to a. This is simply confirming that if you start with a and you first plug it into the inverse function, it's going to turn it into b. But then when you plug b back into the f function, then it go right back to a. Same is true for the other direction. So we're going to be doing f inverse of, and let's compute f of a first. So here's f, plug a in for x. So we just get 3a plus 2. But now we're going to take this 3a plus 2 and plug it into the f inverse function. Y right there is going to turn into a 3a plus 2. So you have a 1/3 times a 3a plus 2. That's where the y was, minus a 2 and parentheses. Now I can remove those inner parentheses and cancel the 2's. So an intermediary step would just be doing 1/3 of 3a. And a third of 3a just goes right back to a. If I started with a and I plugged it into f and then I plugged that into f inverse, I get right back to a. This will always happen when you have two inverse functions. Their composition cancels each other. Determine if the function below is 1-to-1. If so, find the rule of the inverse function. Then compose the inverses in both directions. Okay, to determine if this is a 1-to-1 function, we're going to graph the function. It's a 1/x graph that's been stretched, reflected, and then shifted up 5. So there's a horizontal asymptote at y equals 5, and a vertical asymptote at x equals 0. Okay, so the purple is our actual function. Does it pass the vertical line test? The answer is yes. Does it pass the horizontal line test? The answer will also be yes. So this is a 1-to-1 function. 1-to-1, check. If so, find the rule of the inverse function. Okay, so our first step is to change the g of x to a y. So we have y equals 5 minus 2 over x, and now we simply just solve for x. So I'm going to add the 2 over x to the left side and subtract the y to the other side. I'm going to invert both sides, so x halves is equal to 1 over 5 minus y, and then I'm going to double. So x is equal to 2 over 5 minus y, and that is my inverse function. G inverse of y is equal to 2 over 5 minus y. Now let's do the compositions. And let's use a as our input just to get away from x's and y's. So let's do g of g inverse of a. So this is saying the same thing as doing g of g inverse of a. So I'm going to take g inverse, which is down here, and change the y to an a. So this is doing g of 2 over 5 minus a. Now I'm going to take that 2 over 5 minus a and plug it into the g function. So I'm going to plug it in for that x right there. 5 minus 2 over 5 minus a. Now when you invert and multiply and simplify this, this means you get 5 minus 2 times 5 minus a over 2. You can see that the 2's are going to cancel, the negative will distribute, so we're going to get 5 minus 5 plus a, we're going to get a. Check. Now let's do the reverse composition. G inverse of g of a. This means we're going to be doing g inverse of g of a, which means we're going to be doing g inverse of, and now let's plug a into the g function. So we're going to plug a into this, in other words, a is going to go right there. So 5 minus 2 over a. Now we're going to take that result, 5 minus 2 over a, and plug it into the inverse function. So this y right here is going to become 5 minus 2 over a. So we had a 2 up top over a 5 minus y, and y is 5 minus 2 over a. Okay, so I've done that composition correctly. Distribute the negative in the denominator. That's the 5's are going to cancel. You're going to get a 2 over a down here. Invert and multiply, so it's 2 times a over 2. And sure enough, we get right back to a. Check. Okay, so we have in fact found the correct inverse. Next one, determine if the function below is 1 to 1. If so, find the rule for the inverse function. h of t equals t cubed plus 2. I know what t cubed looks like, and just add 2. So the basic look of this is, and the question is, does it have bumps like this where you would fail the horizontal line test? So you have to think closely, well, what did t cubed look like in the first place? So here's a graph of y equals x cubed. If you add 2 to it, that just shifts it up 2. But this graph will pass the vertical line test, and it's going to pass the horizontal line test. This flattens out at that point, but then it keeps going back up. So it's increasing, flat, then increasing. It never becomes decreasing. You don't get this happening, where it decreases a little bit, and if it did, because then you would fail the horizontal line test. But this graph is 1 to 1. Okay, so we change the h of t to a y, so y is equal to t cubed plus 2, and then solve for t. So subtract 2, so you have t cubed equals y minus 2, and then cube root. T is equal to the cube root of y minus 2. And this is our inverse function. H inverse of y is equal to cube root of y minus 2. Now we do the compositions. H of h inverse of a. Okay, so that gives me h of h inverse of a like this. H inverse of a is cube root of a minus 2. Now I'm going to plug this expression in for that t in the h function. So the h function will cube it. So we have the cube root of a minus 2. That's going to be the input for the h function. Going to be cubed, and then 2 will be added. Well, if you cube a cube root, they cancel. So you just get a minus 2, and then you add 2 to that, and you get a. So check. In the reverse direction, h inverse of h of a. So we're going to do h inverse of h of a. So plug a into the h function. We'll do that part first, and we get a cubed plus 2. Now plug a cubed plus 2 into the inverse function, into this one down here. So we're going to get the cube root of, the input is a cubed plus 2, and then we're going to do minus 2. And you see the 2 and minus 2 cancel, so we just get a cube root of a cubed. That gives us a again, check. Now the next one, determine if this function is 1 to 1. Well, this is a balanced rational function. It has a horizontal asymptote at a third, vertical asymptote at 0. Y is equal to x minus 1 divided by 3x. And let's hit the home button, see what this looks like. It has a horizontal asymptote at a third. I know that because I just divide the leading coefficients. And the denominator is equal to 0 when x is 0. So that's going to be our vertical asymptote. But the green graph is our function. It passes the vertical line test and the horizontal line test. So we have another situation where we have 1 to 1 function. So we change the m of x to a y. Now we solve this for x. Now the tricky thing is that x is in multiple places. You could split the 3x up, put x over 3x minus 1 over 3x, and then that'll get x down to one place, and then you solve for it. Let me show you another way to do this. I'm going to multiply the 3x to this side, so we have 3xy is equal to x minus 1. Gather the x terms together, so 3xy minus x is equal to negative 1. Factor the x out, and then divide. So this is another way to get x isolated. And be mindful that you could also multiply top and bottom by negative 1 and write it this way. Okay, so our inverse function here, this was m inverse, input of y, and it's 1 over 1 minus 3y. And let's do our compositions. M of m inverse of a. So this is going to be m of m inverse of a is 1 over 1 minus 3a. Now plug that into the m function. There's two different x's here in the m function, and this has to go in for both of them. So we have 1 over 1 minus 3a minus a 1 all over 3 times 1 over 1 minus 3a. So we have this nasty complex fraction, and the easy way to simplify it is to multiply top and bottom by 1 minus 3a. So when you distribute this 1 minus 3a to this fraction, it cancels with that 1 minus 3a down there, leaving just a 1. But then multiply to here, times it by 1, but don't forget that subtraction. So we have minus parentheses 1 minus 3a. And in the bottom, this 1 minus 3a is going to cancel with that one, leaving just a 1 times 3, and just a 3. Now distribute the negative. The 1s will cancel. You'll get 3a over 3, which boils back down to a. Check. And now let's do the other direction. How about we just say, for time's sake, I'll leave it to you, but you should also show that when you do this direction that you wind up getting just a again. And I'll leave it to you to confirm that. Let's go to the next one. Determine if the function below is 1 to 1. If so, find the rule of the inverse function, then compose the inverses in both directions. T squared minus 4 is a shifted down parabola, so it has a shape like this. This is not 1 to 1. It fails the horizontal line test. So this has no inverse function, and we're effectively done with this slide. If it's not one-to-one, no inverse function. Now look at this one though. This one's very similar to the last one, except it's cropped. T squared minus 4, but graph it only for t bigger than 0. So we only have half of the parabola. This is one-to-one. So we're going to find the inverse function. Change a p of t to y, t squared minus 4, and then solve for t. So I'm going to add 4 and then square root both sides. So normally you would get t's plus or minus the square root of y plus 4, which is a problem as far as functions are concerned. Because if you input a y coordinate here, like 0, you get a 4 there, and square root of that's 2, you get 2 t's. And that's not good for a function, which is why this condition here is important. T can only be positive or 0, which means that we're never going to accept that negative answer. So we just have this as a result. T is the positive square root of y plus 4. And that is our inverse function. P inverse of y is equal to square root of y plus 4. And for this one here, I'm going to do the composition in just one direction as well, but I'll leave it to you to do the other. Let's do P of P inverse of A. So it's going to be P of, first do P inverse of A, so plug A into P inverse, and we get square root of A plus 4, and then plug square root of A plus 4 into this P function in for that T. So we get the input is going to be squared minus 4, and the input is radical A plus 4. So when you square the radical, they cancel, you get A plus 4, and then minus the 4, we get the A. And then again, you should verify that if you do the composition in this direction, that you also just get A. Okay, and that wraps up our discussion on inverse functions, how to find them, and what they mean, what they accomplish.